Hello, this is Dr. Pods, and today I want to show you how a half-bridge digital power electronic amplifier works. This is a revolutionary circuit that started in about the 1980s, and it really progressed the way that power electronics is used in everyday life nowadays. I will explain to you why that is, but let's first start with how this circuit is structured. On the left-hand side we have two voltage sources, a positive 12 volt source and a negative minus 12 volt source. And at the core of the circuit we have these two MOSFETs. They are digital switches, and they switch our output point here either to plus 12 volt or to minus 12 volt. For obvious reasons, you don't want to turn on both MOSFETs at the same time. And the way this is handled is with this driver logic that we have here, which is controlled by our digital input signal here. So this signal makes sure that only one MOSFET is on. If this is 0, the bottom MOSFET is on, and if the signal is 1, then the top MOSFET is on. They are called high side MOSFET and low side MOSFET. And then we have here an inductor which just acts as a filter and will remove these rapid fluctuations that are caused by the switching. And we have a load. In this case I use a motor, but it could really be anything. You can control light bulbs, resistors, heatings, motors, transformers, magnets, whatever you like. So let's see how the circuit operates. We can start this in my favorite tool here, Every Circuit. And we can see at this point the input signal here is 1. You can see the green line, that is the 1 input signal. And you can see the top side MOSFET here is active, and so our output is connected to the plus 12 volt. And after some time this will switch, and then we will have a change in the input signal from 1 to 0, because that's how I have programmed it. We'll see now this signal has become 0 and the bottom MOSFET was on. So this will happen again. You can see the switching with the bottom MOSFET. The low side MOSFET becomes active, and it switches our connection point from plus 12 volt to minus 12 volt. If we want to, we can actually watch this connection point here. You can see it is either plus 12 volt or minus 12 volt, and it switches controlled by this input signal. And then we have the inductor here. The inductor removes these voltage fluctuations from the motor, because the inductor, as you know, resists current changes. So it's trying to find a steady current flowing through the motor. And now the interesting bit is, in order for this current to be steady, the average output voltage, which is the purple line here, the voltage connected to the motor, needs to be equal to the average voltage at this connection point. And we can control the average voltage at this connection point by figuring out how long we switch on the high side MOSFET and by how long we switch on the low side MOSFET. At the moment you can see that here 80% is the high side MOSFET and 20% is the low side MOSFET. I have programmed that here in this digital source. You can see that here it says width 80%, so for 80% of the time it's on, and for 20% of the time it's off. And so what we get at the output, if you speed this whole simulation up, it converges quite nicely. We get an output voltage of roughly 6 to 7 volts. That is 80% from the whole 24 volts. So 80% of 24 volts, but seen from minus 12 volts. So 80% along this minus 12 to plus 12 volt scale that we have here. If I go down to, for example, 50%, so I take the middle, that should be exactly 0. So we are right at the middle of our voltage range, which means we are fluctuating around 0 volt. Or I could go down to, say, 30%. Let's say 25%. And at 25% the output voltage is minus 6 volt. Of course I can go all the way down to 0 if I like. And if we are at 0, you can see only the low side MOSFET is ever on. And now the motor is running backwards. If you go higher, and say we go towards 100%, You can see now there's current flowing in a positive direction through the motor, and the motor is going forwards. Okay, so this is a qualitative analysis of the circuit, but maybe we want to know a little bit more. We want to know how this circuit, why the circuit is so important. And it is because if you look at it carefully, there aren't any losses in this circuit. You might say, well, how do we do this? We have a 12-volt input and we have a 6-volt output, for example, if I go back to 75% here. So we turn 12 volt into 6 volts without any losses. With a resistor that would be easy, but we would burn off half of the energy. This circuit does it without any losses. Why is it without losses? Because every MOSFET is either on or off, so there are no losses there, apart from very, very minor losses in the MOSFET itself. And the inductor is just a storage element, so again, it doesn't create any losses. The way that it works is, and the key to this is in fact the inductor. So while we have the high side on, there is current flowing through the inductor, and this is increasing the energy in the magnetic field in the inductor. And as you switch to the other side, as you switch to the low side MOSFET, this energy is then released and put back into the motor. So we use the energy storage in the inductor to capture the excess voltage, the difference between the 12 volts that we have at our power supply and the 6 volts we have at the motor. This difference, this energy is stored in the inductor and it is released when we switch to the low side MOSFET. So that means this circuit is essentially lossless. In principle, it is lossless. That is one of the reasons that it is so phenomenally popular. In practice, of course, it is not entirely lossless. And I just want to demonstrate this very quickly. So in order to demonstrate this, I will delete the motor here and I will put a resistor in here. In fact, I will put two resistors in here. So we have resistor number 1. This is our load. It could be 100 ohm, it could be somewhere in that region. And we have resistor number 2, which need a bit more space here. Say it is 1 ohm. So why have I put two resistors in here? The 100 ohm resistor represents our load. It is what is being used in terms of energy. This 1 ohm resistor represents our losses. And I've only used one resistor here. Actually, it represents the resistance of the high side and the resistance of the low side MOSFET, which we assume to be identical. Because only one of these is ever on, we don't have to create two resistances in our circuit. It is perfectly fine to put just one resistance into the circuit to represent both of these MOSFETs, the losses in both of these MOSFETs. Now we can run our circuit, and you can see it still works as intended. So we have to show our signal here again. We need to increase our inductor here a little bit because we have changed the size of resistance. So I'm going up to 1 Henry here. So we get the same behavior as before. We get this nice switching. We get the averaging from the inductor. Maybe I go to 500 millihenry. You can see how it converges to a reasonably steady output voltage. And you can hopefully see how there are no losses anywhere in the circuit. The only losses are in this 1 ohm resistor. Now, because we know the output voltage, because we know the output current, this makes it quite easy to calculate these losses. And in fact, you can just look at the relationship between these two resistors. The 1 ohm resistor will have hundredths of the voltage and therefore hundredths of the power of the 100 ohm resistor in the same circuit. So our losses are approximately 1% in this case. That is a very good result for a circuit like this. Typically you would find losses in the range of 3 to 5% for a well-designed half bridge. But you can see, even 95% efficient means the circuit is highly efficient. You do not need a lot of extra power power the circuit, and critically you do not generate a lot of heat, which makes the circuit very easy to use and integrate into gadgets, consumer devices, cars. This circuit is essentially everywhere. You will find it at the heart of any power electronics device, and there are billions and billions of these circuits out there in the world operating and doing their job. So I hope that was useful. I hope you've liked this short introduction into a half-bridge circuit, and please have a look at my other videos on YouTube.